So good morning, everyone. This is Mohammad Abdul Qader. I'm a PhD student working with Professor Antonio Nani and Professor Ramanthan. Oh, yeah, sure. As I was saying, I'm Mohammad Abdul Qader. I'm working with Dr. Nani and Dr. Ramanthan. And today I'm going to show some preliminary results we are doing for a study related to the durability and mechanical properties of concrete using produced water. Okay, which one is it? This one? Okay. Okay. Yeah, perfect. So to give you a little bit of a background, all of you know that concrete is basically generated in huge volume worldwide, including United States. In 2024, we casted more than 379 million cubic yards of fresh concrete, and this basically means a lot of fresh water, which is something that basically we need for many other uses. So we need to think about different solutions. One of the solutions that are, or one of the things that are available and can be used is basically something called produced water. And for you who works in oil industry knows exactly what is produced water. It is the water that is basically generated during extraction of oil. There are lots of numbers actually out there about how many barrels of produced water is usually generated for barrel of oil. Sometimes they say that it's 20 barrels of produced water, but in general, let's say it's 4 to 7. That's based on one of these studies. And last year, more than 25 billion, yes, billion, not million, billion barrels of produced water were produced in only top 10 states in this country. That's a huge, huge, huge amount of water that can be used in many different sectors. Unfortunately, it's underutilized. So concrete can be one of these industries that can use that type of water. So there is a huge potential for this. So now let me move to the study. I mean, basically, what exactly we did. So we casted 5 different concrete mixes to try to evaluate the performance of that produced water in concrete. We casted 5 different, basically, mixes, as you can see. Okay? Yeah, sure. But basically, yeah, so we have one reference mix with fresh water and then 4 mixes with produced water. For the naming, just to make it our life easier when we are presenting results, let me explain this. So the first number in the naming of the mix is basically the target design strength at 28 days, either 5 KSI or 7 KSI. And then the letter that is exactly after the number indicates the type of water used, either fresh water or produced water or H. H indicates a blend of 50-50 fresh produced water. So it can be P, 100% produced, F, 100% fresh, H, 50-50. And then the 2 letters after that can be either LC, which is lime curing, or PC, produced water curing, produced lime curing. So we had 2 different types of curing, basically, regimes. And then any letters after that indicates a special modification. We have only one mix with a special modification, which is the 5000 mix, that have air-entraining admixture in it. So for the methods or for the testings that we have basically done, we did lots of different testing, including fresh properties. We measured slump and then slump retention after 60 minutes to see how produced water might actually affect the long or the slump after like 1 hour or 2 hours or so on. We did compressive strength at 4 different ages, 3 days, 7 days, 28, and 56 days. And then we also measured electrical resistivity. It might not be a good reflection of the durability of these mixes, but we generally also did that to make comparison between the produced water mixes themselves, because in that case, it's well going to be actually reliable. We have also measured the chloride migration coefficient, non-steady state chloride coefficient, migration coefficient according to the test at 56 days. And we also measured the porosity or permeable pore volume in these mixes at 7 and 56 days to see how the pore structure of these mixes made with produced water is basically changing. So let me just jump directly to the results. Here we can see the slump results in the chart. Basically, the red line represents the slump after 60 minutes for different mixes. You can see the mixes on x-axis, and then the black line is the slump directly after casting. We can see that produced water mixes, in general, have slightly higher slump. That's not very high, but slightly 1 inch higher slump. Most probably, this is related to the to the dissolved salts, helping or aiding the PCE admixture to work more effectively. As we can see the results, simply the produced water is not really impacting slump in a bad way. That is the message. Then we can see here basically the air content, which is the red line on the left axis, and the fresh density. Again, fresh density that was not affected at all by produced water. The last mix is basically have a slightly lower fresh density and higher air content. That makes sense because we added air-entraining admixture, so that's expected. But as we can see, air content also is slightly higher in the case of produced water mixes. But again, what we can see here from this slide, produced water is not really affecting the fresh properties badly. Here we can see the compressive strength results for only first three mixes. The three mixes that are exactly the same, the only difference is the water. Either fresh water, produced water, or a blend of 50-50 fresh produced. So what we can see here is that produced water actually decreased the compressive strength slightly for at different testing gauges, in average of 8 to 9% decrease in compressive strength compared to the 7,000 mix that was made with the fresh water. Again, that decrease, I mean, at 8 to 9% is kind of acceptable in our industry, as we know. So it's not really that bad. In this slide, we can see exactly, again, the black line, which represents the fresh reference mix, but this time compared to the two other mixes, the one that was made and cured in produced water and the 5,000 air-entraining admixture mix. We have two exciting things here. First is that the mix that was designed for only 5 KSI at 28 days actually reached 7,000 at 7 and 28 days, okay? But the other thing that is also very kind of impressive here, or maybe actually bad, is that the mix that was made and cured in produced water have 27% reduction in compressive strength. That means curing itself is playing a very important role here. Making concrete with produced water and curing them in lime water only decreased the compressive strength by 8%. But when we cured them in produced water, the decrease was 27%. Actually, we decided to do the curing in lime produced water to decrease or to limit leaching. But it seems that the opposite happened. Something is wrong, okay? So that is the main thing we can see here, is that curing regime plays a very important role. That was, as I said, the one made and cured in produced water. So as we can see, this figure just shows the percent decrease in compressive strength of these different mixes compared to the reference mix, fresh water mix. And these two mixes are identical. One of them have only 8% decrease, cured in lime water. The other one that was cured in produced lime water have 27% decrease. So that is basically the main thing we can see from here. In this figure, we can see one-to-one comparison. So the x-axis represents the compressive strength of the fresh water mix, reference mix, okay, at different ages. The y-axis represents the compressive strength of those different mixes, okay, at different testing ages. So we can see that almost all the mixes were actually within the 15% margin line when they are compared to the freshwater reference mix. The only exception, again, is the mix that was made and cured in produced water, which is out of the 25% margin line. Again, curing seems to be very important. Here we can see the bulk electrical resistivity results. Again, as I said, it's kind of hard to say that that test is reliable in case of produced water or even seawater, because chloride is presented in a huge amount in these types of water. Therefore, it does not really show you the refinement of the microstructure. The only thing, I think the only application for electrical resistivity in case of seawater or produced water that is helpful is going to be comparing different mixes made with seawater or produced water and see how the electrical resistivity is different between them, but not really making a comparison of a freshwater reference mix and a produced water mix. But anyways, there is a decrease of 43 to 53% in case of these identical mixes that have the one only difference, which is the mixing water. Here again, we can see the same thing, but with the two other mixes. Again, the mix that was made and cured in produced water showed the highest decrease in electrical resistivity of about 64%. That is the max, the red line. Basically, I mean, you would expect that the 5,000 PSI mix should have the lowest or the most decrease in electrical resistivity, but it is not really the case here. Here we can see the chloride migration coefficient, the NT-BOLT 492, which is the non-steady state chloride migration coefficient. So we measured it for only 3 mixes. We are still doing testing. So as we can see also, as we are increasing the content of produced water, there is a higher coefficient, okay, of chloride diffusion. But it's not a linear relationship because as we can see, both 7P-LC mix and 7H-LC mix are showing very comparable results. Yes, the 7P-LC shows kind of higher chloride migration coefficient, but it's not linear because here it's 100% produced water. In the 7H-LC, it's 50%. And here we can see the porosity results or permeable pore volume. We did, I think I mentioned that TP135, ash to TP135, where we are measuring the porosity of hardened concrete. So we can see that almost all the different mixes are doing the same. They are very comparable. The only difference is that the 7PPC mix, again, the mix that was made and cured in produced water, have a smaller, slightly smaller value for the porosity. And here we comes with the hypothesis, actually, we developed for what is happening here with curing and mixing with produced water. So that makes, actually, we believe that there is some sort of salt crystallization inside the pores of the 7PPC mix. That resulted in a decrease in the porosity, and also because of the salt crystallization, that applied some stresses, internal stresses, that decreased the compressive strength and also decreased the electrical resistivity. Again, I mean, this is the hypothesis we have at this point. It requires further testing to kind of like further enhance our view about that. So to summarize and conclude what I said, we have used here produced water for making some concrete mixes. And we did lots of different fresh properties and basic mechanical properties testing. What we can say is that fresh properties are not affected by produced water. Mechanical properties, when the only variable is the type of water, the decrease in compressive strength is not really that bad. It's 8 to 9%, again, accepted in concrete industry in general. But again, curing seems to have a very big role, and that's part actually of the future work that I'm going to talk about in the next slide. So from a durability point of view, yes, we did some durability testing here, but I think it would be way more beneficial and meaningful to do some direct testing for durability, and this, again, will going to be part of the future work. Because again, electrical resistivity, chloride migration coefficient, these might not be very reliable. Why? Because you have already high chloride content inside this water. So how come, or what are you exactly comparing when you are comparing them with the freshwater mix? So for the future work, we are planning to cast more concrete, different target design strength, different water to cement ratios. We will going to add lots of different supplementary cementitious materials, maybe biochar to see how produced water works. We will going to also, again, that's a very big part of the study at this stage, is we will going to try to investigate the role of the curing, using produced water as a curing regime on mechanical properties and also on durability performance. The durability, as I said, we will going to do some direct durability measurements and testing, things like drying shrinkage, autogenous shrinkage. We also will going to study the early hydration, let's say, behavior of these mixes to see how produced water also is impacting that. At the end, I want to extend our thanks to Dr. Nevin from ExxonMobil. I'm not sure if he's here, but I can't see him. But thanks for his help and oversight over this project. Thank you for listening. I'm happy to take any question.